All right, and welcome back to Cognitive Psychology. This is week 13, class number 2. And today we're going to begin our look at chapter 12, problem solving and creativity. So we're continuing to look at the higher order cognitive processes now. This time we're going to focus on how is it that we solve problems. When we encounter things that we don't know the immediate solution of, what are the cognitive processes that help us eventually attain that solution? In other words, eventually help us solve that problem. We're going to begin again, staying with that theme of defining what we're looking at. We're going to start off with what is a problem, and we're going to take a look at an example of a few, and we take a look at a specific type of problem called Wordies. We're then going to take a look at how do we solve these problems? What is it that we cognitively do when we solve problems? And we're going to take a look at some of the things that we do with the representations in our mind that can either help us solve a problem or hinder us from solving a problem, either make a problem easier to solve or much more difficult. So the first one we're going to take a look at is restructuring, actually changing how we represent a problem. Then we're going to take a look at functional fixedness, the fact that we might try to use traditional solutions in a way that is not beneficial for a particular problem. Then we're going to take a look at mental set, the phenomenon where if we keep doing things in a certain way, our mind is going to want to keep doing them in that exact way, and that can hinder problem solving. And then we're going to take a look at incubation effects. This is an effect where you leave a problem that you've been struggling with, and then when you come back, all of a sudden, there's a solution. So we'll take a look at what might be going on in that situation. And then we're going to end it with a look at a specific type of or category of problem known as insight problems. And we're going to set those up to try to understand what is it that makes those so difficult to solve. All right, so let's start off with what a problem is. So in psychology, in cognitive psychology, a problem requires 2 criteria to be met. First thing is that there has to be an obstacle between your present state and your goal. There has to be an obstacle between where you are and where you want to be. So that's number one. There has to be some sort of hindrance between where you are and where you want to be, your present state and the goal. And then the second criteria is that it can't be immediately obvious how to get around that obstacle. So this kind of captures the idea of we need to come up with a solution. The solution is not immediately apparent. So those are the 2 criteria that we need in order to actually have a problem. So in cognition, that is what a problem is. And some of the most early work done on problem solving was Kohler back in 1927 when he literally got stranded on an island, and there was chimpanzees on the island, and he thought, you know, I'm going to improve my situation and just start doing some experiments on chimpanzee problem solving. So let's take a look at a video that shows one of these chimpanzees trying to solve a problem, and we are going to see that this one involves trying to get food using a stick. And again, note the definition there. Actually, we're going to take a look at a few problems, but note the definition of a problem and how each of these situations is a problem. Because in each situation, there is a gap, there's an obstacle between where the chimps currently are, their present state, and their goal, which in most cases is food. So there's always some obstacle. The food is too far away. The food is too high up. The food is behind a wall. And then also notice that the solution is not immediately apparent. So these chimpanzees have to go through a process because it's not immediately known to them how it is that they are going to achieve their desired goal. All right, so here we can see a chimpanzee trying to reach bananas that are suspended high above, higher than the chimpanzee can jump. So if the bananas were close enough for the chimpanzee to jump, this wouldn't be a problem because the solution would be immediately obvious. Sure, there's an obstacle between the present state and the goal state, but the obstacle is easily solved because the chimpanzee can just jump up there. This, on the other hand, is a problem. The bananas are too far away the chimpanzee needs to figure out how to handle it. And in this case, the chimpanzee is trying to stack boxes in order to reach their goal. So they're trying to remove the obstacle, too much distance between their present state, which is on the ground, and their goal state, which is getting that banana. And you're probably wondering, is this going to be the time? Come on, chimp. You can do it. There you go. All right, goal state achieved, banana in the hands. So there you can see, the basic definition of a problem. The goal state was not immediately apparent on how to get to that goal state from the present state. Here's another example of a problem. The banana this time is hidden behind a wall, not immediately apparent how to reach a banana that is too far away. So this chimpanzee has to come up with a solution. Can't just reach for it with a stick, but has to place one stick inside of another to reach the banana. Again, not immediately apparent, fits the definition of a problem. So you can watch some more of Kohler's monkeys if you're interested. The link is in the downloadable student lecture slides. But those two examples illustrate the basic idea of what a problem is. So once again, you have a present state where you are. In this case, for the first monkey, behind a wall. In this case, for the second monkey, on the ground. You then have a goal that you want, in both cases bananas, and it's not immediately obvious how to remove an obstacle that's in your way. So in the first case, the banana is behind a wall, it's too far. How do you remove the obstacle of too far? In the second case, let's get that one centered. The bananas are too high. How do you remove the obstacle of too high? And again, sometimes the solution is not going to be immediately apparent. Sometimes it's going to be use a stick. Sometimes it's going to be stand on crates. So we need to try to figure out when we're problem solving, how are we going to remove that particular obstacle? All right, so that was Kohler's monkeys, and we're now going to put ourselves in the place of his chimpanzees and try to solve some problems of our own. So what I'm going to do is, for the next few slides, I'm going to give you, what I'd like you to do is pause the video and give yourself a chance, maybe give yourself like 2 to 3 minutes to try to solve each of these following problems. So the problems are called Wordies. And what these are, they're picture word puzzles. They'll illustrate some common phrase or word. All right, so the example that I'll show you to kind of let you know what how these work. So here we have a picture. So whatever's in the box is the picture word puzzle that you're trying to solve. And here we have Daffy, Donald, and Mallard. And you might be wondering, like, what is the phrase that this is trying to communicate? And the solution comes when we realize that Daffy is a famous duck. Donald is a famous duck. A mallard is another word for a duck. So we have a duck, another duck, and a third duck. These ducks are all in a row. So we have the phrase ducks in a row. So that's going to be the sort of challenge for these wordies. So I'm going to go through these. We're going to go through rather quickly. Do yourself a favor, get the full experience of this, pause the video, and give yourself, 2 minutes to try to solve what these wordies are. We're going to see the solutions later, but do go for the full experience. Pause the videos. Here we go on the wordies. All right, so this is wordie number 1. So what is the phrase? What is the slogan? What is the famous saying that is being illustrated here in this picture puzzle? Wordie number 2. So try to figure out the phrase, the slogan, the saying that is being illustrated here. Wordie number 3. So once again, phrase, slogan, saying, what is it trying to say here? And once again, make sure that you are pausing the video if you in order to get the full experience. And then this one is our last one here. So once again, What is this communicating? What is the solution to this word puzzle? And notice your current state is not knowing the saying. Your goal state is knowing the saying, and it's not immediately apparent. It's not immediately obvious how to remove the obstacle between those two. So reading, try to solve the following wordies, is not a problem because your goal state was not reading the sentence. Sorry, your present state was not having read the sentence. Your goal state was reading the sentence, but it was immediately obvious. How are you going to accomplish that? You just read the sentence. It's not a problem. This wordie, this word puzzle, if you haven't solved it yet, you can clearly experience that there is an obstacle between your present state, seeing the word puzzle, and your goal state, understanding the phrase. So we're going to return back to those wordies. I hope you wrote down your answers or your best guesses, made a mental note, because we are going to come back to those in just a bit. But first, we are going to turn to our first look at what is going on when we solve a problem. And this is the idea of restructuring. So in restructuring, the theory is that when you solve a problem, you need to represent that problem in your mind. Somehow in your mind, you need to have symbols and representations that stand in for pieces of the problem, and then you manipulate those representations, and this is that information processing approach. You manipulate those representations until you come up with the solution. Now, the key for restructuring is that some representations that we use for a problem, they make solving the problem easier. Other representations make solving the problem possible. So some of them make it easy, some of them make it possible. On the flip side to that, other representations make it very difficult. Other representations might make a solution even impossible. So let's take a look at let's take a look at this problem right here. So this might have been, I can't remember if we used this for the cognitive warm-up, but if we did, let's see if we can remember what the solution is. So this is challenge number one. What is the number of the parking space that contains the car? So we have a bunch of parking spaces. We have a bunch of numbers there. And your problem is to try to figure out what is the number that one car is covering up. All right, so give this a shot. Pause the tape at this point. Sorry, pause the tape. Pause the video at this point and see if you can solve this. Give yourself, about a minute for that problem-solving experience. This is a really important aspect of understanding that these solutions are not immediately obvious, so that when we see what the solution is, you can fully experience that restructuring of how you thought about this solution. So go ahead and pause the video now. All right, so you're back. Did you get the solution? If you represented the problem with this orientation, you probably really struggled with the solution. If you represented the problem in this orientation, you have a 16, starting from the left, you have a 16, a 6, a 68, an 88, and then you end with a 98. And you were probably sitting there trying to do all this math, trying to figure out, well, what is the function? What is the progression? 16 minus 10, but then you add 62, but then you add another 20. 10. You probably were trying to do a lot of mathematics because you represented this problem in a certain way. You represented it from this orientation. If we restructure this problem by flipping it, all of a sudden it becomes immediately obvious. All of a sudden it's 87 because the numbers are all in a row. 86, blank, 88, 89, 90, 91. Of course, the answer is 87. So that restructuring, that reorienting of our perspective solved the problem. And that's what was required to solve this problem. Now, this is a very obvious case. We had another one that we looked at in our cognitive warm-up challenge where we had the problem about the two trains that are about to collide. One is going 60 miles an hour, one is going 40 miles an hour. They're 100 miles away, and as soon as they begin, a bird flies from one train to the other at 80 miles an hour. And we asked, what is the total distance that the bird will fly before those two trains smashed into each other? And as we saw in the first day that we met in the back in January. If you represent this as a distance problem, you're going to take hours to solve this, and you're going to need calculus to solve this. It's a very difficult problem. Representing it as a distance problem makes this problem a challenge. It makes it very difficult. If you restructure your representation and restructure it as a time problem, then all of a sudden it's seconds to solve this problem. Because if these two trains are going at 60 and 40 miles an hour and they're 100 miles apart, they're going to collide in 1 hour. They're traveling towards each other at 100 miles an hour. They got 100 miles to go. They're going to travel for 1 hour. If this bird is traveling 80 miles an hour, it can cover 80 miles in an hour, and there we have our problem solved. So the idea from psychology is that whenever we solve a problem, what we do is we end up just restructuring it. In our mind, somehow we end up restructuring the problem, and once we represent it in the correct way, the obstacle is removed and we can go from our present state, not having a solution, to our goal state, having the correct solution. Now, we'll give you another example just to sort of show you this representations idea. So we borrowed those two examples from earlier in the semester. Here's a new one, and this is a riddle called Monk on a Hill. So here it goes. At 9 a.m., a monk starts to climb up a hill and spends the next 12 hours hiking to the top. He reaches the top at 9 p.m. and spends the night there in meditation. The next morning at 9 a.m., he starts to descend along the same path he used to climb the hill the day before. Taking his time, he reaches the bottom at 9 p.m. in the evening of the second day. So on day one, he starts at 9 a.m. at the bottom, reaches the top at 9 p.m. On day two, he starts at 9 a.m. at the top, reaches the bottom at exactly 9 p.m. The question is, can the monk descend the hill so that he is not in the same spot at the same time on each day? That is, if he goes up on a Monday and comes down on a Tuesday, can he descend this hill and ascend this hill? Can he do this trip so that at 4:07 on Tuesday, he is not in the same place as he was at 4:07 on Monday? And can he do that so at no point do these times overlap? So this problem can be very difficult depending upon how you represent it, because you might represent it in this way. You might say to yourself, well, what if he runs up the hill for the most of the first day, right? He runs up most of the hill the first day, and then he takes a lot of time for the remainder of the hill, right? He runs up like 90% of the hill, in about 20 minutes, and then he takes 8 hours and 40 minutes to recover and finish that last 10%. And then what if he runs down most of the hill on the second day and then takes a lot of time for the remainder of the hill? Will that be a path where he will never be at the same place on the 2 days? Or what if he runs up the hill, half of the hill on the first day, and then takes a lot of time for the second half, but then runs down most of the hill on the second day and takes a lot of time for the rest for the rest of the hill? So what if he doesn't have the same sort of pattern on the 2 days? What if it's a completely different sort of ascent versus descent? So give yourself a second here, pause the video, try to solve this, try to come up with an answer. Do you think it's possible for this monk to make his trips so that he is not at the same place at the same time on these 2 days? Or do you think it's impossible for him to do so? And try to figure out which one it is. So you can pause right now and take your and give it a shot. All right, so we're back. So if you represent, here's the restructuring aspect of this problem. If you represent this problem as two separate trips, it makes applying the correct operators difficult. What that means is that if you have it represented as two separate trips on 2 separate days, day number 1 goes up, day number 2 goes down, it makes applying the right operators, the right moves, the right processing of your representations difficult to do. However, if you restructure it and represent it as 2 overlapping trips on the same day, then it's very easy to apply the correct operators. So if you don't see it as 2 separate trips, but you restructure it and say, you know what, I'm going to superimpose those 2 days. I'm going to take Monday and Tuesday, day 1 and day 2, and I'm going to look at them right on top of each other. All of a sudden, the problem becomes much easier to solve when you restructure it in that form. So let's take a look at it in this restructured form. So here we have monk on the first day. So this is the monk on day 1, and he's going to take 12 hours to go up the hill. Start at 9 a.m., end up at the top at 9 p.m. Here's the same monk on day 2, and he's going to take 12 hours to go down the hill, start at 9 a.m. on the top and end at the bottom at 9 p.m. So these are the 2 monks on 2 separate days, right? The same monk on 2 separate days. Day 1, he's at the bottom. Day 2, he's starting at the top. Let's take a look at what happens when you superimpose those 2 days. All right. So when you superimpose those 2 days, it becomes immediately obvious that this monk is going to cross paths with himself at some point on the hill. It might differ where that is, depending upon how he goes up and down the mountain, but there is no way that he can make it up and down without passing himself, which means that at some point he's going to be at that same place at the same time. So right about here for these trips is when that monk will be at the same place at the same time on both days. Importantly, there is no way for him to start at the top and go to the bottom without crossing at some point. So this monk will have to be at the same place on the hill at the same time on both days. All right, so we've taken a look at 2 or 3 sort of hypothetical problems. Let's take a look at one from cognitive psychology. And one issue that cognitive psychology has that could be solved, one problem that exists that could be solved with restructuring, is the idea of consciousness. So we haven't touched on consciousness in this course, but nothing that we've done can explain why we're aware of what it is that we're doing. Nothing that we've gone over so far can tell us why we are aware of our experiences. So this derives from the fact that we have based, and cognitive psychology has based much of its work on the physical symbol system hypothesis and on these classic cognitive representations of mental processes. And it could be that these very concepts, the very way that we've structured cognition, is not allowing us to solve the problem of conscious experience. It could be that the very concepts we're bringing have not allowed us to solve the problem of conscious experience. And this is what happens oftentimes in paradigm shifts, right? So psychoanalysis was having trouble answering some questions, so along came behaviorism and said, hey, we're going to restructure psychology. Forget about your unconscious thoughts. We're going to restructure our psychology in terms of the environment and behavior. And all of a sudden, certain problems were readily solved. But then behaviorism came into difficulty. Behaviorism came into issues and problems that it couldn't solve. And along came cognitive psychology and said, hey, we're going to restructure our ideas of behavior, not as just behavior and environment, but as internal representations that get manipulated. And we're going to use this physical symbol system hypothesis. And now cognitive psychology is running into a problem up with consciousness. And it might take the next generation of psychologists in order to say, you know what, let's start thinking about cognition like this. Let's start thinking about in these terms. And then all of a sudden, it could be that the people that are struggling with consciousness right now and understanding why is it that we even have consciousness, once that restructuring occurs, they might say to themselves, oh my goodness, it's so obvious. This is what consciousness is all about. Remains to be seen. All right, so that's restructuring. The next thing we're going to take a look at is functional fixedness. So restructuring was something that helps us solve a problem. You're struggling with a problem, you restructure it, you then are able to solve it. Functional fixedness is something that doesn't help. It hinders our solving of a problem. And functional fixedness refers to when you restrict the use of objects or the use of concepts to their familiar functions. And that restriction does not allow you to solve a problem. So if you ever want to see people breaking with functional fixedness, all you need to do is look up hacks online. Just go online and look up lifetime hacks, and eventually you're going to come across people breaking functional fixedness with everyday items. So for example, the use of a fork is typically to eat food, right? That is functional fixedness. If you think that, to use a fork, what do you use a fork for? You use it to eat food. What is a fork good for? It's good for eating food. How do we use a fork? We use it to eat food. That's restricting this fork to its typical function. But what if you have a cork stuck in a bottle? Well, you can solve that using a fork. But if you restrict your use of a fork to just eating food, you'll never come up with this solution. What if you need to reheat your onion rings that you got takeout for? Well, if all you think about a fork is eating those onion rings, you're going to be restricted by functional fixedness, and you'll never come up with this particular solution. And if all you think about in terms of forks is that they're for eating and eating alone, well, then you'll never be able to contour makeup in in those exact details. Good luck getting that perfect cat eye without being able to break that functional fixedness and use a fork for a non-familiar function. So oftentimes when you are having difficulty with a problem, it's because you're trying to solve that problem and you're using the most common representations, using the most common ways to think about that problem, using the most common concepts in order to try to solve that problem. And that's what's making it difficult, because those common typical concepts or common typical representations are not helping. They're not the way to solve this problem. So what you need to do is you need to break that functional fixedness in order to solve this particular problem. So we took a look at functional fixedness in terms of a fork. We're now going to take a look at functional fixedness in terms of a hole in the wall. So this is a great little example from a Japanese game show that really illustrates functional fixedness in action. Now we're going to set it up with this premise over here just to show you that there are certain ways about thinking of these representations. So if you saw a wall like this, if you were walking down the street and all of a sudden you saw a wall with this human-shaped hole in it, you know exactly how that human went through that wall, right? You know exactly where their arms went. You know exactly where their head is. You know exactly where their legs went through that wall. And our minds, if we're functionally fixated, they will try to go through that wall, through that hole in the wall, using those spaces for their arms, for their heads, and for their legs. And we're going to take a look at a Japanese game show that plays on that to try to make these problems challenging for their contestants to solve. All right, so we are going to take a look at that. All right, so we're going to take a look at that right now. So this is human Tetris. So enjoy the competition. And again, take a note at problems that are being solved by these contestants using functional fixedness, using traditional concepts of where should your head, where should your body go, and then look at ones where they break functional fixedness and we're able to solve the problem.
ルールは簡単。プレイヤーは様々な形に繰り抜かれた壁を的確なポーズですり抜けられると10ポイント獲得。しかし、抜けられない場合は壁に激突、哀れみ水の中へ。頑張って頑張って。お楽勝。さあ、コンビ合いコンビ合い。手なんかいらないで多分。手いらないんだ。いいアドバイスだったいいアドバイスだった。さあ、コンビ合い。息の合ったところどうか。無理だ。これ難しいね。さあ、よく考えて。脳を使って。さあ、どうか。抜けたらクリア。そうしている。さあ、これは難しいような。弾丸ジャッキいけない？さあ、弾丸ジャッキいけるか？どうする？どうする？おっと、しゃがみ弾丸ジャッキさあ、脳を使ってこの形。脳を使ってこの形。 くんですけどね。ドライブです。これはドライブのイメージです。さあ、文字像どうする文字像。
難しいよな。一瞬で
この後、東京スターチームが文字を文字像を共に成功したのに対し、田舎チームは包み文字、イザ文字と連続で失敗。個人戦最後の田舎西の挑戦が勝負のキーポイントに。
これは無理でしょ。
ロサ会館が迫ってきた。長身の2人が立っている。さあ、ロサ会
All right, so we'll pause it right there and analyze some of these instances here to see how functional fixedness stopped some of these contestants from solving their problem, and how breaking functional fixedness actually led to a solution. So we'll start off with one that was successful that actually did not involve functional fixedness. So this is almost like the control condition here. And you can see that this contestant here, when he's staring down this hole, there's nothing human-shaped about this particular hole. There's no outline of a head. There's no outline of arms. This is a block. This is like a block C, letter C. So there's no functional fixedness to bring to this problem, right? There's no kind of like fixating on the idea that, oh, there's a cutout of a head. My head must go there. There's a cutout of legs. My legs must go there. And if you recall, he successfully solved this problem. He was successful in going through that wall. So no functional fixedness. He was free to use whatever sort of representations and solutions and functions came to mind. Now let's take a look at another example. So we have this cutout right here, and we'll zoom in a little bit. And on this one, this representation or this cutout activates functional fixedness in your representations. Because you can clearly see that this is kind of like a baby sitting up, and it has human shapes to it. So you can clearly see that that's where the head of this, human outline is supposed to be. This is where the legs are, right? This is a human-shaped outline, and because of that, this individual fell for functional fixedness, tried to put his head where the head cutout is, tried to put his legs where the leg cutout is, and as we saw, failed to solve the problem, was not able to solve the problem because of functional fixedness. Now, this one is particularly illustrative because they actually give you the correct solution. They actually show you how this problem should have been solved, and it's there in the bottom left corner. So let's zoom in on that, and you can see in this case that they show an outline, or they show a diagram of a contestant where they're supposed to go. And importantly, it's a little difficult to see, so let me help you out here. He's lying on his back with his legs spread. So that's the head of the contestant right there. And to correctly solve this problem, you got to break functional fixedness, not put your head into the head cutout, but put your head where the middle section, where the groin basically of this cutout is. And then the knees are right there. So the knees have to go through the bottom leg part and the shoulder part. Again, not the functional fixedness where we typically say knees go in knee holes, feet go in feet holes, heads go in head holes. But you have to break that functional fixedness to correctly solve this problem. And then we saw a case where there was functional fixedness. So once again, this looks like an individual sitting in a car driving. And once again, it's an outline of a human, which activates that functional fixedness of, oh, there's the head cutout, so my head must go there. There are the leg cutouts, so my legs must go there. There's the body orientation cutout, so that's where my body must go. However, this contestant was able to break functional fixedness, and this problem became incredibly easy to solve. He basically said, I'm not going to put my legs where I think where this hole is saying my legs should go. I'm not going to put my arms according to functional fixedness where my arms should go. And he just stepped right through that. It was one of the easiest solutions once you're able to break that functional fixedness. All right, so that was functional fixedness. That was a hindrance to problem solving, made problem solving harder when you fixate on the traditional functions for representations and objects. Next, we're going to take a look at a related idea called mental set. And this is where you bring preconceived notions on how to solve a problem, mostly because the same solution has worked before. So you try to solve a new problem by bringing back previous solutions that had worked in the past. And if those previous solutions do not apply to this new situation, it's going to hinder your ability to think of a new solution, to think of a new representation in order to solve the problem. So let's illustrate this with the following riddle. So this is eggs in a basket. So I'll read it out for you. It goes, there are 6 eggs in a basket. 6 people take one of the eggs each. No eggs are added to the basket. How is it that one egg can still be left in the basket? What is going on here? So 6 eggs in a basket. 6 people take one of the eggs each. No eggs are added to the basket. And yet somehow at the end, 1 egg is still left in the basket. So pause the video, try to solve this, struggle through it so that you can appreciate if you might be applying a mental set later on when we go through the solution. All right, so pause the video and we'll start it up again when you get back. All right, welcome back. So hopefully you paused. Anyways, let's keep going on with this. So preconceived notions often come about because they were successful in the past. You tried solving a problem successfully in the past, and you'll continue to try to apply that solution over and over and over again, even if it's no longer going to be successful. And this happened in this egg riddle here. So let's take a look at it step by step to see how our mental set can be achieved. So we know that 6 people take an egg. And we know that at the end of this, there's going to be 1 egg left in the basket, right? So that's our goal. 6 people take an egg, 1 egg left in the basket. That's our goal. So we're going to start solving this problem step by step. And step number 1 is that person number 1 takes an egg. So we're mentally thinking about this and we say, all right, we got 6 eggs in a basket. We want to get it down to only 1 egg in a basket. Person 1 takes an egg. There they go. Take the egg. So now we only have 5 eggs in the basket. Notice that this has been successful. It has gotten us closer to our solution. Taking an egg out of the basket has gotten us closer to a solution. So we're going to try it again. Person number 2 takes an egg. So we got 5 eggs in the basket. We're trying to get down to just 1 egg in the basket. Person number 2 takes 1. And now we're closer. We're closer to our goal. There's only 4 eggs left in the basket. So taking an egg out of the basket has been successful twice. We do it for a 3rd time. Person 3 takes a basket. We're even closer to our goal. Person 4 takes an egg out of the basket. We're even closer to our goal. Person 5 takes that egg out of the basket. We're even closer to our goal. Come on, person 5. There you go. Person 5 takes an egg out of the basket. So now we're stuck with person 6 takes an egg, right? However, we're stuck now because how is it that person 6 can take an egg, but there's still 1 egg left in the basket? And we are having trouble solving this because of this mental set. Taking an egg out of the basket was successful the first time. Taking an egg out of the basket was successful the 2nd time. It was successful the 3rd time. Got us closer to the solution the 4th time. Worked the 5th time. So in our mind, we formed this mental set of we got to take an egg out of the basket. We've taken an egg out of the basket 5 times. Our mind is now preconditioned into this preconceived notion that the way to solve this problem is to take an egg out of the basket. And it's only by breaking that mental set that we can realize that person number 6 can take an egg if they end up taking the egg and the entire basket, right? So there's still an egg in the basket. Everybody has an egg. It's just that the solution for the last step was unlike the solution for the first 5. And that makes it difficult to solve because of this idea of a mental set. We got trapped into a mental set. We used our preconceived notions. And because of that, we were unable to, or it was very difficult to restructure this problem into something that was readily solvable. All right, so that's mental set. We're now going to take a look at incubation effects. So this is now something that can help you solve a problem. This is actually a good strategy to use if you ever are really struggling with something in your schoolwork, for example. If you're trying to write an essay and it's just not happening, sometimes what you want to do is you want to set aside that problem for a particular time. So setting aside a problem for a particular time after you've been unsuccessful at solving it, oftentimes when you come back, the solution will just come to you. You'll get a very quick solution to the problem when you return to the problem. And that is the idea of an incubation effect, right? It's almost as if the solution was incubating in your mind and it just needed a little bit of time. It just needed a little bit of quiet in order for it to rattle around in there in your mind. And then when you come back to the problem, all of a sudden you're like, oh, aha, there we go. That's what the solution was the whole time. So it's solving a problem just by stepping away from it. So let's take a look at the incorrect explanation for incubation effects first. So research has shown that the incorrect explanation for incubation effects is that your mind is unconsciously still working on the problem, that your mind is unconsciously still grinding away, that whatever cognitive abilities are left over, that are not being used, are somehow just grinding away at this problem, and that the time away allows that process to occur so that when you come back, you can solve the problem. That's actually the incorrect explanation. That's what people typically intuitively believe. But a better explanation, or the current best explanation, is that what is happening is that this time away is allowing you to restructure this problem. This time away is allowing you to break functional fixedness. This time away is allowing you to break your mental set. Basically, this time away is allowing you to forget those inappropriate strategies that you were using that were brought about because you were trapped by these set effects. You were trapped by mental set. You were trapped by functional fixedness, so you couldn't restructure this problem. So in that spirit, we're going to try again to solve the following wordies. And what I would like you to do is give it another shot and see if you can solve them now that we've stepped away from them for a particular point in time. So once again, give this one a shot right now. So I'll give you about 10 seconds. We'll see if the solution immediately pops up, and then I'll tell you what the solution is. All right, so give it a shot. All right, so that was 10 seconds. If you came up with the solution after failing the first time, that's an incubation effect. So if you haven't come up with the solution yet, the solution for this wordie is 3 blind mice, because that top word is mice with no I. The middle word is mice with no I. The bottom word is mice with no I. That's 3 mice with no eyes. If you have no eyes, you're blind. 3 blind mice. All right, so let's try to solve the next one. Again, I'll give you 10 seconds. All right, so that was 10 seconds. This one, you have a 9, you have a 5 and a 5. You have 1 9 and you have 2 5s. That's 9 to 5. So if you work a regular office job, you are working 9 to 5. If you're a fan of Dolly Parton, you know the song 9 to 5. 9 to 5 is the phrase here. All right, so this next one, particularly challenging. Let's see if you can get it in the next 10 seconds. All right, that kind of felt like 10 seconds. I'll be honest, I lost count. So this one is particularly difficult. And if you were unable to solve it before, but you could solve it now, that's incubation effects, right? Again, you forgot about your old strategies, forgot about the old ways of thinking about this problem, and we're able to bring new strategies by taking a break and forgetting about those inappropriate strategies. So for this one's particularly difficult because the word that you're looking at is sight. So that is sight, not psi, but sight. Unfortunately, the end of the word is missing, right? There is no end to this word sight. So the T has been removed, there's no end. There is no end in sight. So this is the phrase, no end in sight, particularly difficult. Maybe you got it. Now, weren't able to get it before. If that's the case, that's an incubation effect. All right, and the last one here, once again, 10 seconds. All right, so we're able to solve it this time around after not being able to solve it before. In any case, I'll give you the solution right now. So the word is vators. However, there is a space between the D and the E. There's a space in this word. The word is vators. This is space invaders. So the phrase is space invaders. And once again, if you were able to solve it now, but you weren't able to solve it when you first saw it, that break in between where we were talking about other issues with problem solving, that is the incubation effect. All right, so we're going to wrap up today with a look at insight problems, and this is going to set up for next class where we're looking at the information processing approach to problem solving. So we'll first talk about the category of insight problems, and an insight problem is a problem where people are oftentimes unaware that they're close to a solution. It's a problem that oftentimes only requires one step, and they're called insight problems, or also known as aha problems, because oftentimes they're met with that feeling of, aha, I have it. Aha, I've got it. You know, the famous eureka, you know, I've solved it. And sometimes with a problem, you know when you're getting closer to the solution, right? So the eggs in a basket problem, you knew you were kind of getting closer to that solution. However, other times it's very difficult to even know you're getting close to a solution until you just get that insight and you're like, aha, there it is. That's an insight problem. So let's take a look at an example here. It's called the haystack problem. And the problem states the haystack was important because the cloth ripped. Why did the cloth ripping make the haystack important? So try to solve this. Pause the video. Why did a cloth ripping all of a sudden make a haystack important? So pause the video now. Try to come up with a solution. And when you come back, we'll talk about this insight problem. All right, so welcome back. So there could be numerous reasons why a cloth ripping could make a haystack important, right? Maybe the cloth was carrying hay. Maybe they were carrying hay to go feed the cows, and the cloth ripped, and all the hay fell out. So now the haystack became important because they had to get more hay. Maybe there was the proverbial needle in the haystack, so they needed a needle to sew up the cloth. So all of a sudden the haystack became very important. Maybe there's thousands of other possibilities in terms of why a cloth ripping could make that haystack important. However, the one that is the correct solution and the one that leads to that aha moment is when you realize that the cloth is actually the cloth for a parachute. And if that rips and you're the parachuter, all of a sudden that haystack becomes immensely important. That's where you want to land in order to save your life. So again, this just requires one step. The step is realizing that the cloth is a parachute. Once you have that, you go, aha, that's why the haystack was so important. So I'll give you one more before we wrap up for today. And this one was going around on social media about a year ago. This is called the funeral problem. So I'll read this one out, see if you can get the solution. So this is a story about a woman. While at the funeral of her own mother, she met a guy whom she did not know. She thought this guy was amazing, so much the dream guy that she was searching for that she fell in love with him immediately. However, she never asked for his name or number, and afterward could not find anyone who knew who he was. A few days later, the girl killed her own sister. Question, why did she kill her sister? So this was a problem that was going around on social media, and this was framed as a psychopath test because apparently it's not true. Don't fall for those. But apparently, if you could solve this, that meant that you were a psychopath or at least had psychopathic traits. So why did she kill her sister? You know, after meeting this guy at the funeral, not knowing his name, not knowing his number, why a few days later did she kill her own sister? Try to solve the problem. Pause the video, and I'll give you the aha solution in just a moment. All right, so welcome back. Did you get the solution? Were you able to figure it out? And did you feel that aha moment when you finally did figure it out? So why did she kill her sister? Well, the answer is she reasoned that if the guy appeared at her mother's funeral, then he might appear at another family funeral. So killing her sister was just a way of bringing this guy back, to the funeral home, bringing this guy back to a place where she could find him. And apparently, the belief was that if you came up with this solution, with this aha solution, it reveals psychopathic traits. Again, that's not true, but this is one of those aha solutions. You probably had other ideas about why she might kill her sister. Maybe she got angry at her sister. Maybe she found out that that was her sister's fiance, and now she was free to, pursue him. But the correct answer is that she figured that if he was at her mother's funeral, he might come to another family funeral, and this time she could get his name and number. All right, so we're going to take a look at why these problems are so difficult, because they are, but they only require one step. Why is a one-step problem so incredibly difficult? Well, that's my little teaser for what we're going to cover next time when we take a look at problem spaces and problem solving, the information processing approach to problem solving. So that's going to be it for today's class on Chapter 12, Problem Solving and Creativity. So come join us next time when we're going to take a look at problem spaces so that we can understand why these insight problems are so difficult and how do we navigate problem spaces in order to solve difficult problems. But that's it for today. So thank you so much for joining me on this week 13 class 2. Take care of yourself, and I will see you next time.